Bob Sleeve called me about a month ago to ask me if I would be willing to do this, which of course is always nice to come back to Edmonton. He asked me not necessarily to talk about forestry, which is what I do. So I had to come up with something that was a little bit more, I guess, applied to this session, which was clean energy. And so one of the things that we are looking at doing over the next year or two is to work with the Alberta government and the government of Canada in terms of looking at monitoring large areas, specifically related to the oil sands development, both in situ and surface mining and reclamation. So what I'd like to do is present some of the work that we're doing, not within the context of forestry per se, but really with an eye towards how we can apply these methods to looking at large-scale industrial disruptions of the natural environment. Okay? As a sort of embedded in that, we'll be looking at the fusion of multiple sensor data, because I'm a firm believer that we're not going to be, we can't just look at one sensor. One sensor, as Nicholas said upstairs earlier today, one sensor isn't going to tell us everything. One sensor will give us one slice of information, but we need multiple data sources to really give us a full picture of what's out there. Okay, so our activity, my lab activity at UVic has really focused since 2005 on this whole idea of sensor fusion and data fusion, not so much sensor fusion, but data fusion, information fusion. So that's how I will put this in context. Okay, so I like using this analogy that remote sensing is like a really good stew, right? We can have the ingredients, right? Meat, vegetables, gravy. Meat provides protein, vegetables, fiber, gravy, flavoring, right? And individually, you can use any one of these ingredients and you can eat them and they're fine, right? But they don't give you a stew. So, remote sensing and multi-sensor remote sensing is very much the same way. We have our ingredients. In this case here, we have a fixed wing system, and we have a set of small sensors located right in the back of this Navajo. We have it's very sophisticated, but they're small. We have a full range imaging spectrometer. We have a laser system. We have digital cameras that you can't see, and we have an inertial navigation system. All of this in sort of where they used to put the toilet in the Navajo. Right? We took that out, we drilled some holes in the back, and this is what we have in there. Right? So it's small, compact, and it's a well, I shouldn't say it's a better use of the space, but it depends if you're up there for 6 hours. It's probably not a better use of the space. But I don't necessarily get to fly in it for 6 hours. I leave that to others. Right? So in this system here, we have an imaging spectrometer, and we'll talk a little bit more for those of you who don't know what spectrometers do. We'll talk a little bit about that. It's not going to be a lecture on spectroscopy here, but we will deal with it in a little bit more detail. And with the spectrometer, we collect 492 channels. That's maximum number of channels we can collect. 2 meter spatial resolution. So each one of these channels in the visible and near infrared samples at 2.5 nanometer, and in the shortwave infrared from 1,000 to 2,500 nanometers, about 6 nanometers. Contiguous samples. So we get a full image cube, contiguous image cube. We can define the spectrum. This isn't multispectral. This is spectroscopy. We have actually a 4-return laser system, 150 kilohertz maximum. We never fly to 150 kilohertz, but that's what it's rated at. First and last and 2 intermediate returns. All right, so if we're flying at 1,500 meters above the ground, typically we would collect about 1.25 per square meter, 4 returns per point. That's sort of the nominal posting density that we get. And then we also get intensity, something which we don't normally talk about. It's the intensity return, and we don't use it, right, because we have the spectrometer. But there is an intensity that's collected as a 9-bit signal as well, which gives you a very pretty picture. But I'm not quite sure. We worked with it a little bit initially, but it was really hard, so we didn't work with it. So We tend not to. It's a path of least resistance, right? So if stuff looks to be too hard, we just put it aside for future reference. I'm getting too close to retirement now. I can leave it for the next people to come along to work on the hard stuff. We also have a small frame digital camera in here, which gives us photography that we orthorectify to about 20 centimeters. And that provides sort of a nice background photo map that we can use to look at some of the data and imagery. Tying all of this stuff together, and this is really the brains of the system. This is inertial navigation system, which has an inertial measurement unit, which looks at the attitudinal issues of the aircraft, and then a GPS, which looks at positional issues and the height. So those are one set of ingredients. And then, of course, that was in the fixed wing, and then we have exactly the same thing in a helicopter, slightly different. So if the first one was a beef ingredient to a stew, this would be lamb, right? It's a little more flavorful. It's nicer than beef. Oh, sorry. But,
you're in Alberta.
I know. Lamb's pretty good too, right? It's got a little bit more flavor. So with this helicopter system here, we have exactly the same, well, almost exactly the same components. We have a spectrometer in there, we have a laser in there, and we have cameras, right? The laser is a 260 kilohertz system as opposed to 150. This flies lower. So rather than getting 1.25, 1.5 points per square meter, we're now getting 12 points per square meter, 4 returns per point. So we're essentially getting 50 returns per square meter without overlap. The spectrometer is a visible near infrared, it's so 400 to 1,000 nanometers, and we get about a meter spatial resolution, 200 plus channels, and then 10 to 15 centimeter photography. And that's from the helicopter system. So slightly different ingredients, but the stew is the same, sort of. Right? And so this is the recipe, right? So this is the processing thread that we developed to put these ingredients together. So this is our recipe. So we have a simultaneous, and you can't really read this because it's decimated, so I'll read it for you. Simultaneous hyperspectral LiDAR data acquisition, and this is carried out by our partners. Now we've partnered with a private company out of Sydney, BC, Terra Remote Sensing. They do an awful lot of flying in Alberta and BC, South America, Central America, primarily helicopter-based flying, but they bought a fixed wing for this project. And they supply the LiDAR, they supply the INS and the camera, and we supply them with the spectrometers. We've also done the development of the software to put all this together. So the LiDAR components include calibration. This is what Terra essentially typically does. Classification and filtering. So what we want to do is we want to identify what's ground and what's not ground, right? Or buildings, whatever. And then filtering of that, we can create a bare earth model, and you've seen all this stuff before, so I'm not going to go into it in detail. We also create what's called a top reflective surface model. Okay, and I'll get into why we do that in a bit, but we do that with the orthorectification of our hyperspectral data, and increasingly we're using this to orthorectify our photography as well. But from the other data we do, we create a canopy height model. Now, a canopy height model, as you probably know, is a terrain normalized set of vegetation points, and we remove the effects of the ground, so we're only looking at veg height here. And then we generate biometrics. Nicholas alluded to some of them. We use pretty much the same metrics that he used. We don't use the same software. We started this, as I was saying earlier, we started this in 2005. And our first day, we got a disk delivered to us that had a file with a point cloud on it. And it had X, Y, Z, intensity, class. Whether it was ground, veg, basically ground veg. And they said, here you go. Right? There was nothing out there, absolutely nothing out there. So we sat down and we figured out, we started working through, and got a couple of the grad students to start working on it. Ben was there at that time, and we ended up building a software suite initially out of IDL, which is a sort of I guess a third generation programming language. It's an object-based programming. It's like MATLAB, but it's used for visualization. Envy is built, for those of you who use it. and the image processing system is built with IDL. We built all of our software in IDL to start working with this. One of the things that we built was a biometrics package. Now that biometrics package looked at both the vertical and the horizontal structure within a grid cell. Okay, so we're using a grid-based approach to doing this initially. And we looked at the distribution, I'll show you that in a minute, the vertical distribution of the point cloud, and we looked at the horizontal distribution as well to look at the gas structure. And so we have a canopy-based biometrics package. We've subsequently also built a terrain model-based metrics package as well, which generates sort of the basic metrics, slope aspect, curvatures, soil moisture, landscape drainage, whatever we want to call it, relief, and then we upscale. And they're tied together so we can upscale to 20 meters the terrain metrics, and they're tied to the biometrics, the canopy biometrics, so we can look at them in uniform. Right? And so once we do this, we get a series of models that we can then use for applications, so structural classifications, inventory, ecosystem-related models, etc. From the hyperspectral point of view, we do radiometric processing, we remove instrument noise, sort of typical image processing. We do a radiance to reflectance conversion. We have a Modtran base, for those of you who know this. It's a radiator transfer model package. We initially used an off-the-shelf product at core, but it wasn't everything we wanted, so we spent the last year taking the Modtran code and getting it to run with our data very specifically, and it's now doing what we want it to do. So we generate reflectance data directly, and then we orthorectify the data. And we orthorectify to the top of the reflective surface model, because typically when you orthorectify photography, when you orthorectify imagery, you do it to a bare earth model, because that's what you're supplied. That's what you're always given. You know, any 20,000 mapping product that you're given, SRTM, all this sort of stuff, it's all a bare earth model. Right? They assume that the ground is somewhere down there, and that's the height they give you. Well, for 2 meter data and 1 meter data, the vertical displacement is significant for a tree. So what we want to do is we want to orthorectify the optical data to the actual surface that it's reflecting off of, not to the bare earth. Right? So what we've done is we've developed this bare earth reflective surface model that we ingest into our orthorectification procedure, and so that what we're tying the hyperspectral data to, or any of the optical data, the photography, whatever, we're tying it to the surface reflectance. We've also now developed or redeveloped this orthorectification, taking advantage of GPU technology, the graphical processors, so that we can do a visual orthorectification, real-time orthorectification, and alignment, which is kind of neat. But that's a different story. So in the past, this is what we wanted, right? Our bare earth model. This is really what we wanted to look at. Everything else was thrown up. You know, people would do, with the exception of transmission line studies, where they're interested in the catenaries and modeling the sagging catenaries with increased energy transmission through the lines, and then looking at the vegetation underneath it. You guys at the Geological Survey, all you're really interested in is this stuff here. So we threw all of this really neat stuff away. Right? We just discarded it. Nobody could care less about it. Right? But this is really interesting stuff to work with. It's fun stuff to work with. Right? And this is really where we want to go. And as an aside, we've been doing a lot of this work now for some of the forest companies on Vancouver Island and increasingly on the mainland. And they say, hey, look, you know, fly the LiDAR survey for us. That's great, because our engineers, cut block location, road planning, all this stuff, that pays for the survey. Right? Anything you do on top of that in terms of inventory modeling and yield prediction, all the stuff that Nicholas was talking about, that's gravy. The survey's already paid for. Right? So we just finished doing 300,000 hectares of helicopter data for one of the local forest companies on Vancouver Island. and massive amounts of data. But I mean, they're saving millions of dollars just in terms of their cruising, their cruise service. They don't have to do. So it's great data to work with. It's fun data to work with, and we shouldn't throw it away. Right? So this is what I call my level 1 data. This is the orthorectification process here. So here we have the LiDAR data. Here are 3 sets of data. The LiDAR point cloud underneath here we have the ground, and this is a DSM. This is not terrain corrected. So here we have the LiDAR point cloud. This is helicopter data, and these two verticals here represent field mapped trees. So the guys went out and we told them we wanted really accurate positioning of the trees, right? Because we wanted to bring those back. We wanted to know what the species were and whatnot. So this represents the location and the height of the field map tree, right? So this is supposed to be down here. So clearly the field component needs a little bit of work. But on top, superimposed on top of this is a 1 meter hyperspectral data set. So you can see here's the top of the tree, defined by the LiDAR laser. And the brightest pixel should be the top of the tree in this case, or very close to the top of the tree. So, you know, we're typically within half a meter. These are 1 meter pixels, right? So we're typically within a half meter, which is pretty good. You know, on the field crews too, you can't take too much away from them. They can't see the top of the tree, so it's kind of hard for them to measure the height of the tree. Right, so they give a general estimate, and they might be a meter or 2 off, but positionally they're not bad. So this shows really how well, at a plot level, how well these data work. And at a larger scale, we see that in fact these trees are, or these data sets are positioned very accurately. So this is our 2 meter hyperspectral data, which has been superimposed. This is fixed wing, so it's superimposed on top of the 1.5 meter, 1.25 meter LiDAR data. So you know, you can look at the edges. There's shadows in here, but you look at the individual small trees in here, and it's pretty accurate. You know, it's within a pixel. So we're at 2 meters. You know, people say, well, it's not very accurate. But God, you know, what have you guys been working with? Just think about that. Right. So back to the food theme. This is not a recurring theme. This is the only other time I would actually break it out. I like to think of our data as an onion, right? It's built in layers. If the core of the onion is bad, then everything else is going to be bad too. I mean, there's not much you can salvage from the outer parts of the onion if this part here is rotten. Well, it's the same thing with your data. If this is your data collection and it's pooch to begin with, then nothing you do to it out here is going to help it. Right, so we do take an awful lot of care in the acquisition and the processing, that initial processing of the data. We spend a lot of time doing that. We spend a lot of effort in just pulling these data sets together so that before we start running any information extraction on these data, we know that the data are the highest possible quality we can get, and that the positioning is the highest possible quality. Right, so this is what we're looking at here. So here's our internal core, and this is the acquisition of the data. Right, the first level of processing out here, we deal with still with data. Okay, we're not at the information stage yet. We can still probably go back and convert these sets here back into the original data set. Right, so we have a bare Earth model, a canopy height model, and a hyperspectral image cube. I didn't include the photography. Once we leave this level and we go out here, now we're starting at information. So this is all information extraction. So from the bare Earth model, we get slope, aspect, curvatures, soil wetness. Now soil wetness in this case is strictly a geometric model. It's based on the upslope drainage area divided and normalized by the slope gradient. This is stuff we were doing U of A 1980 something, 84, 85, right? But we've resurrected it, and it actually looks quite well. We have the computers now to be able to run it within a reasonable period of time. The canopy height model, and again, back to Nicholas's stuff. I mean, and as he said, you know, we've been through this now, so we know what we're doing, right? So we all basically do the same thing. We do a canopy mass, what I call a canopy mass model, which looks at a grid-based model, which looks at all of the points within the point cloud there and works out the metrics based on a 10, 20, 40 meter, whatever grid cell you're working with, or single tree. And we do work with single tree, but we work with the fixed wing data and with the low density data, we only get the position and the approximate height of the tree. We don't do anything else with it. With the helicopter data, we can do a lot more. But and I'll show you how we use this in a minute. And once we have this first level of information, then we can get into some of the actual applications models that we were interested in. So we look at, for example, veg health, chlorophyll content. We've been working with pine beetle, sort of after the horse has left the barn type of scenario. But be that as it may, I'm sure there will be some other bug that will come back that will present us with exactly the same scenario where we want to get at them early on. Right? As soon as the pine beetle was done, we had spruce budworm, we had hemlock looper, we had the whole 9 yards. So there's hardly a conifer left in central BC now. If you drive through central BC, it's all deciduous or sick conifers. Right? Wetlands mapping is important. Habitat, productivity, forest inventory, and fire fields. I mean, these are the sorts of things that we're working on from a forestry point of view. Right? And it all stems from the same data set right at the core. And that's why it's so important to get this right and to get this right so that you can start looking at these things. Once you leave the data to information stage, there's not much you can do. Right? So, the types of products. Go a little bit faster here so that we don't run out of time. But again, this is what Nicholas was showing you, right? What we have here is a 50-meter grid cell, and these are all the LiDAR points contained, fixed-wing LiDAR points contained within the 50-meter grid cell. If we organize these in terms of height-frequency relationship, we don't even have to go into the quantile basis at this point, but just look at height-frequency. We can see that, and this is a Doug Fir stand, old-growth Doug Fir stand in Vancouver Island. We see that the tops of the trees are about 65 meters or so. Right? And so here we have the tops of the trees here at about 65 meters. And then we hit a mass of points up in here, which represents this upper canopy. We have a second mass of points in here, which is probably a secondary hemlock type canopy. And then we have this understory here, which at about 10 to 15 meters, which is probably another hemlock canopy underneath there coming up. Right? We can see these in these distributions here, and we can describe these distributions. And one of the things that we're working on now is looking to see, for example, if we can start mapping height to live crown underneath here, directly, automatically, by looking at these distributions and the shapes of these curves. The spectrometer gives us a different data set completely. So Nicholas again was right. I mean, it's hard to keep saying that Nicholas is right. That's frustrating. But he always goes first for some reason, probably because he's more of a showman than I am. But he's right that we've gone now from detecting. He used correlation, but it's really using MSS type multispectral satellites. We couldn't really measure much. We could detect whether something was there or not. And we spent from 1972, when the first Landsat satellite was launched, until now and beyond, we're still using multispectral data, and we're still trying to tease out these statistical relationships. Right? We're not doing much better. So we're still looking at NDVI as being sort of the be-all end-all of indices to map everything. Well, it maps nothing. You get out on the West Coast and you get an LAI of 2 or more, and NDVI saturates. I mean, so there's got to be more to it than that. So the hyperspectral gives us an opportunity, because we're dealing with contiguous spectra. We can start making measurements. We can start coming up with some very, very sophisticated models and some very sensitive models, which gives us information on things like health. Gives us very accurate species identification based on the shapes of these spectra, not just the positions of 4 points in space, in spectral space, but gives us 490 points in spectral space. We can start coming up with shape metrics, which are very, very detailed. There are three components to these spectra. The first is the continuum, which is sort of the general shape of the curve. And it'll give us some information. And really that's what we're abstracting the continuum when we're working with MSS data. Right? So we're looking at sort of the general shape. More importantly are these absorption features. And these are really what's diagnostic about the spectra. So we have an absorption feature here, which is our pigment feature, really detailed. And we can look at the shape metrics in here and come up with whether we can look at species in there, we can look at health, we can look at nitrogen, we can look at carotenoids, we can look at chlorophyll, the whole 9 yards. We have water features up in here. Now these are leaf water. There's cellular scattering features in here. They're not atmospheric water. So once we get rid of these two big puppies here, which are atmospheric water features, once we get rid of those in the Radiance data, we still have these features up in here. And the depth of that gives us some indication of how much water is in the leaf. Right? So if we're starting to look at health issues where desiccation is a result, we're starting to look at these features disappearing. We could argue when those shapes start to happen, but the reality is they do start to happen. And once we move further out, we're looking at cellulose, lignin, and other issues in chemistry. For those of you who are in the geology vein, from 2000 to 2500, we have all of the mineral absorption features. Right? So in terms of doing mineral exploration and all this good stuff, this is the area that we want to work with too. A whole bunch of absorption features out there where we can look at the shapes and we can very diagnostic of the mineral content. So these are really very, very useful things to have. And we're generating thousands, if not millions, of these spectra for every flight line that we're running.